is Irina Bobrova, PhD, and she will tell us about classification of non-Abelian Painlevé equations. And I would like to ask you to start with a short introduction, general introduction to non-Abelian Painlevé equation before classifying them.
Sure.
You're welcome. Let's begin.
Thank you a lot for the invitation. Yep, and first of all, I would like to start with some historical remarks about Painlevé equations. The idea of the Painlevé equations is the following. So we know that some special functions can be defined by ordinary differential equation, and the problem of classification in classical case is to define new special functions by ordinary differential equation of some order, mth order, and with properties that generalizes properties of elliptic functions. In order to solve this problem, the Painlevé property was introduced. It means that our general solutions of given ODE should be in some sense good. Or in other words, they have no critical movable points. And in the case of the second order ODE, this problem was solved by Painlevé and his co-authors. They have found 50 classes of such ordinary differential equations, and later Gambier had shown that only 6 of them define new special functions. And these special functions are known now as the Painlevé transcendents. Here I present some of them. The master equation, the Painlevé 6. This equation is a second order equation, and it contains 4 arbitrary complex parameters. The Painlevé 2 equation is this one, and it contains only 1 parameter, and the Painlevé 1 equation has no parameters. So, for some, why these equations define new special function, these equations for some parameters, for some special values of parameters alpha, beta, gamma, and delta can be reduced to known classical special functions. And today we will focus on the first Painlevé equation. So several properties of these equations that I would like to mention are the following. They can be they have isometric representations. Namely, they can be written in this linear system with some matrices A and B. And this system is compatible if and only if matrices A and B satisfy this relation that is also called as the zero curvature condition. The Painlevé equations are Hamiltonian, and they are related to each other by the degeneration procedure. So by some change of variables with a small parameter, we can reduce points of the Painlevé 6 to the Painlevé 5, and so on. Well, before we go to non-Abelian case, let me make a short overview of this topic. So, as I know, the first examples of non-Abelian Painlevé equations were obtained in the paper by Balandin and Sokholov, and they have obtained matrix analogs for the Painlevé 1 and Painlevé 2 equations. Yeah, and by a similar technique, this classification was done for the second Painlevé equation in the recent paper of Adler and Sokolov. So, yeah, there are some examples of non-Abelian in the sense of matrix. In the matrix case, Painlevé equations, they were obtained by Kawakami. He considered Schlesinger type isomorphic deformations, by which he obtained the sixth Painlevé equation in the matrix case, and then reduced it to lower Painlevé equations, and many other stuff. Well, and in this topic we did the following. We also have classified the Painlevé. The matrix Painlevé for equations. We study for the Painlevé 4 equation. We study its quasi-determinant solutions, and I will describe what it is a little bit later. Yep, and with the series in the series of papers with Vladimir Sokolov, we classified non-Abelian Painlevé equations with commutative parameters in this series of papers. Yep, and today we will focus on this paper where we used the symmetry approach to classify such equations. Well, and I also would like to. I also will give some summary of this paper, of the recent paper with Vladimir Retach, Vladimir Rubtsov, and Georgy Sharikin about non-Abelian discrete Toda chains. So by using a reduction procedure, we can obtain from non-Abelian discrete Toda chain some examples of discrete, of non-commutative discrete Painlevé equation. Well, why we would like to study non-Abelian Painlevé equations? Well, it's known that in the commutative case, there is, in the commutative case, some very famous and important PDE can be reduced to the Painlevé equations. For instance, the KdV equation can be reduced to the first Painlevé equation or to the Painlevé 2 equation. The Sine-Bardon equation can be reduced to Painlevé 3, sorry, and so on. So this integrable PDE have analogs in the matrix case. For instance, matrix KdV equation can be written in this form, and it was obtained in the paper by Vadati and Kamindru. They had used the inverse scattering method in the matrix case. It's also known that this matrix KdV equation has a hierarchy of commutant symmetries, and it also has the zero curvature representation with some matrices U and V. So we know that KdV in the abelian case can be reduced to the Painlevé 1 equation. Now we would like to make the same reduction for this matrix analog of the KdV equation. Yep, here I write down explicit form of matrices U and V. These matrices depend on the spectral parameter mu. Yep, matrix KdV equation has the same symmetries as in the abelian case. And for instance, if we consider this vector field, global invariance of this vector field, we can reduce the matrix GDEq equation to the first Painlevé equation. And this reduction were considered in the paper by Olver and Sokholov. So, namely, again, if we take this change of variables, we can reduce this equation to the case of ordinary differential equation that can be integrated one time. And as a result, we can obtain a matrix version of the first Painlevé equation. And here, A is an arbitrary matrix that arises from the integration from the integration. So we can do the same reduction for the matrices U and V. Namely, if we supplement this change of variables by this formula for the spectral parameter in order to introduce new spectral parameter lambda, then we can obtain from matrices U and V new matrices A and B that are given by these two formulas. And one can verify that this compatibility condition for the matrices A and B leads to the matrix Painlevé 1 equation. So we have derived matrix analog for the first Painlevé equation. This analog solves matrix GDEq equation. This analog also has isomodromic representation. In the paper by Balandin and Sokholov, it was shown that the matrix P1 equation admits a matrix analog for the Painlevé-Kovalevskaya test. It also has Hamiltonian structure. So the Hamiltonian structure is given by this function with the constant canonical Poisson bracket. And it can be rewritten as a system of two first-order differential equations. Well, but instead of the matrix algebra, we can consider arbitrary algebra. Namely, we can consider associative unital algebra A that contains variables U and V, and this algebra is variables U and V and our constant matrix A. It's also a non-Abelian parameter over the complex numbers. And since we would like to generalize matrix systems of ordinary equations to the non-Abelian case, we will equip this algebra with a derivation that satisfies the Leibniz rule. Yep, and here we have some small remark that thanks to this non-Abelian parameter A, we can introduce a new variable Z bar in order to write down so-called fully non-Abelian version of the Painlevé 1 equation. Yep. Then after this change, this becomes just Z bar. And now we have equation now we have the following question. Well, what about other Painlevé equations and how to implement into them non-Abelian parameters? So, how to classify them? Here I would like to present some methods that we have used in our papers. So the problem is the following. We would like to define a commutative analog for the some Painlevé equation that satisfies the following properties. Under commutative reduction, this analog should coincide with a given Painlevé equation, and it should be integrable in one or in some sense. So we will work with unit associative algebra A over some field with zero characteristic, and we equip this algebra with a derivation that satisfies the Leibniz rule, and for any parameters from our field, the derivation of this element should be equal to 0. There are at least 3 criteria that are useful in this classification problem. Matrix Painlevé-Kovalevskaya test, but I will not describe it today. Auxiliary autonomous systems and quasi-determinants. In the case of auxiliary autonomous systems, we assume that if we have this equation for which we would like to write down its non-commutative analog, we assume that variable y is an element of the algebra A, and variables z and t are elements of its center. We also assume that all parameters that Painlevé equation have are commutative sorry, it should be F, from field F, or they may belong to the algebra A. And we also going to write down for a non-Abelian analog the Mandromic Lex pair, and we assume that the spectral parameter in this Lex pair also belongs to the center of this algebra. Well, in case of the quasi-determinants, we need to change algebra A by a division ring. And one more property that we will consider is that independent variable is also an element of this division ring, such that its derivation is equal to 0 or is equal to 1. But in this case, we can work only with constants that are abelian. And as before, the spectral parameter also belongs to the center of this ring. Well, and we will say that the non-Abelian analog for the Painlevé equation is integrable if it satisfies at least one of the criteria above, and if it admits in the Mandromic representation. So we divide our classification problem into 2 parts. We first find some candidates that can be integrable, and then we will search. We will try to find their Mandromic representation. So let me start with this criteria. So in this method, we assume that all dependent variables belong to algebra A, and all independent variables are elements of its center. We also will use a non-abelization procedure. It means that we can, for instance, rewrite this abelian term in the non-abelian form. It is given by this expression, and alpha is an element of the complex field. So in order to find integrable in order to find a candidate for a non-Abelian analog of the Painlevé equation, we need to construct a criterion that selects, we need to construct a criterion. Then by using this criterion, we will classify non-Abelian analogs for the autonomous versions of the Painlevé equation. So yes, Painlevé equations are non-autonomous, but we will first consider their autonomous versions, classify non-Abelian analogs for the autonomous versions, and then we will restore, and then we will recover from the autonomous version its non-autonomous version. And then for a non-autonomous version, we will find its isomandromic Lex pair. Yep, let me move to some detail. So in the commutative case, as I said, all Painlevé equations are Hamiltonian, and this Hamiltonian and their Hamiltonian have the following form with different functions f, and with h1 and h2 that are polynomial in variables u and v. So the corresponding motion equations have this form where p1, p2, and q1, q2 are also polynomial in u and v. So since this Hamiltonian is non-autonomous, it's not a first integral of motion. It's not the first integral for this system. But if we freeze the independent variable z, then we can rewrite this system 9 in the form 10. Here u and v are here u and v depend on new variable t, and z is a parameter, arbitrary parameter. Well, yep, and since this system has isomandromic Lex pair, we can reduce it to the isospectral Lex pair for its auxiliary autonomous system. Let us look at this auxiliary autonomous system. So now this system is also Hamiltonian, and the Hamiltonian can be obtained from the formula 8 by freezing variable z. So since this system is autonomous, one can verify that the Hamiltonian is the first integral of the system, and we will call this Hamiltonian an Okamoto integral for the auxiliary autonomous system. This system also has a hierarchy of commuting symmetries. These symmetries can be written in this form with different k. With different k. And one can also write down a Lex pair for this autonomous system. So the last two properties are trivial because the Hamiltonian is the first integral, and we can fix it. And then by rescaling of variable tk, of the corresponding variable tk, the system 11 coincides with system 10. And the Lex pair given by equation 12 will coincide with the Lex pair, the spectral Lex pair for equation 10. But if we consider non-Abelian variables u and v, these two properties are no longer trivial. So again, in the non-Abelian case, we are going to consider a unit or associative algebra A over the field C. We assume that variables u and v belong to this algebra. Let us consider elements z, t, and tau. They are from the center of this algebra. And we also assume that all parameters belong to the field. Since we are going to work with non-Abelian analogues for the ordinary differential equations, we need to equip A with derivation. So let dt, d sub t, be notation for the derivation of our algebra A that, as before, satisfies the Leibniz rule and such that dt of t is equal to 1. Then non-Abelian ODE system.
I'm sorry, just a stupid question. Are you sure that the differential should commute and not enter? Usually they commute with the minus sign.
I'm sorry, could you please repeat your question?
Я по-русски скажу. Дифференциалы вроде должны антикоммутировать, а не коммутировать. Или это не дифференциалы, а производные просто?
Это просто производные, просто производные.
Это просто все, спасибо.
Да.
Все, ага.
Да, мы просто хотим, чтобы у нас были не только элементы u and v from our algebra, but also u prime, u double prime, and so on.
Понятно. Спасибо.
Well, then this system we will call a non-Abelian ODE system, where f and j are some elements of our algebra A, and the system has a symmetry, non-Abelian symmetry of this form. If these two derivations of our algebra A commute with each other, namely, we will look at this condition. That is similar to the Abelian case. So let us consider the following example. So instead of system 13, we can consider this system with two variables u and v, and one can verify that this system will be this system is the symmetry of the first one. So we just need to compute this condition. So let me describe the symmetry approach in this classification problem. So the idea is the following. We first find integrable auxiliary autonomous systems of the Painlevé type, and then we'll recover the corresponding Painlevé systems. So this method is based on the following steps. We first construct non-Abelian ansatz for the auxiliary system and for its symmetry with K1. Then we require that these two systems commute with each other, and this condition leads to the restrictions on the unknown coefficients. Solving this system of algebraic equations for known coefficients, we obtain a finite list of solutions, and for a given finite list of non-Abelian system, we reconstruct the corresponding non-Abelian Painlevé system. How to reconstruct it? We just replace t by z and restore f and z in the system. And now we denote d sub z of u, u prime, and d sub z of v, v prime. well, for instance, for the Painlevé system, one can verify that its symmetry with K1 is given by this huge system, but under the commutative reduction, it becomes to system 17, and here we can see our Hamiltonian for the first Painlevé equation. Well, yes, and there are also two criteria that are also useful in the classification problem, but the symmetry approach but the symmetry approach allows us to classify to obtain non-Abelian Painlevé systems that contain all known examples of the Painlevé type of such systems and some new. Well, yep. Let me briefly describe our classification results. So, in each case of the Painlevé type, the corresponding Painlevé type, we find a huge number of systems with symmetries. For instance, in the case of the Painlevé 6, there are 35 systems that satisfy this property. But thanks to the group that act on this list, we can select 8 orbits of this action, and it means that there are only 8 non-equivalent systems of this type. And for instance, in the case of the Painlevé 1 equation, there is only one analog of this. There is only one analog that satisfies this property. Yep, and as I said before, this criteria is more general than the criteria of Hamiltonian systems and criteria of systems that and the criteria of systems that have Akamoto integrals. But I'd like to stress that our Hamiltonian systems that are also contained in this list are a slight generalization of the Kawakami system because they are invariant under the S3 action. Yeah, but let me skip this detail. Well, what I also would like to say, all our systems have a zero curvature representation, and they are also connected with each other by a degeneration scheme, by a degeneration procedure that can be can be done as for the systems and for systems and for their leg pairs. Yep, and also what I wanted to say is the following: our systems are closed under this degeneracy procedure, and they are also closed under this group action. Yep. If there are no questions, I would like to go to the second part of this talk.
Yes, please.
Yes. Now I would like to present another tool, how to work with non-Abelian Painlevé systems. So we are going to use quasi-determinants. And in this setting, we need to consider, instead of the algebra, an associative unital division ring over field F with the characteristic, with a zero characteristic, and this field, this ring should be also equipped with derivation. We will denote it by D, capital D, and this derivation, yes, as before, is an F linear map that satisfies the Leibniz rule. It is the main property of this map. Then we also will denote D of F by F prime, and we will fix an element from a special element Z from our ring R, such that Z prime is equal to 1, in order to write the so-called fully non-commutative analog for the Painlevé equation. Yep. And for any scalar parameter, we have A prime. With just 0. So, what is quasi-determinant? A quasi-determinant can be defined recursively by this huge formula, but this this formula generalized to the non-Abelian case, not a determinant, but a ratio of determinants. Namely, if we consider a commutative ring, then this formula 18 becomes to formula 19, where we have just a ratio of two determinants. In particular, if we consider the case of the 2 by 2 matrix over our ring R, then we can find 4 quasi-determinants, and some of them are presented here. Well, in the case of the 3 by 3 matrix, we have 9 quasi-determinants, and one of them is presented here. So why we need to use a division ring? Because in this machinery we have a non-Abelian analogs for the rational functions, and we need to have invertible elements for any given elements that will appear in our construction. So in the paper by Vladimir Retach and Vladimir Rubtsov, solutions of the non-commutative Toda equation were obtained. Namely, they have considered these two chains for negative part, for positive part and for negative part of the Toda equation. And these two chains are connected by these initial conditions with arbitrary functions kappa 1 and kappa minus 1. Well, now we would like to present solutions of these non-commutative Toda chains. In order to do this, let us consider these two series of functions in our ring R, A sub n and B sub n. They are defined recursively by these two formulas. Note that here we have some special order of multipliers. Well, then one can verify that for these two, that if we take these two quasi-determinants and for these two quasi-determinants, and we'll substitute them into these Toda chains, then these quasi-determinants are solutions of these Toda chains for the negative part for the positive part and for the negative parts with general initial conditions kappa -1 and kappa 1. For instance, let us take the case of n1. Then by these two formulas, we can obtain that theta 0 is just b0 in the power -1, theta 1 is a0, and theta 2 is given by this expression. So then we just need to substitute these two guys into positive part of the Toda chain, and we can immediately obtain that these three functions are solutions of this Toda chain with n1. So why we work with Toda chains? Because the Painlevé equations are related to, in the Abelian case, the Painlevé equations are related to these Toda chains. In particular, in the case of the Painlevé 2 equation, Vladimir Retach and Vladimir Rubtsov have shown that this fully non-Abelian analog for the Painlevé 2 equation, here that is an element of our ring R, have solutions in terms of this, or in terms of the quasi-determinants, or in other words, in terms of these Toda chains. If we assume some restrictions for the initial conditions kappa -1 and kappa 1. In the case of the Painlevé 2 equation, these conditions are given by these two expressions. And these two conditions have these conditions have arbitrary, not arbitrary, have this parameter z, independent variable. Then if we construct this solution for the positive part and this solution for the negative part of the Painlevé 2 equation, then we can immediately obtain that this second Painlevé equation with alpha shifted by n can be solved by this expression, and for the negative part, the second Painlevé equation shifted by -n can be solved by in terms of this expression for the negative part. And under the commutative reduction, when y is just a commutative variable and z is also just a commutative variable, these two equations coincide with equations with the corresponding with the corresponding equations for the relation between the second Painlevé equation and abelian to the chain. So using similar idea, we considered a fully non-abelian analog for the Painlevé equation. And this fully non-abelian analog is given by a system of the third order. Well, we needed to consider, let me stress that this system has a first integral. Namely, if we look at the sum of these three equations, we can obtain that f0 plus f1 plus f2 is equal to our variable z. Thanks to this condition for the arbitrary parameters alpha 0, alpha 1, and alpha 2, they are commutative parameters in this case. Well, but we need to work with system of the third order because this element Z is an element of our ring, and the second order, the system of the second order has different terms. Well, what I wanted to say? I wanted to say that if we make a reduction by using this first integral, the parameter z can be appeared in different places in the resulting system. And in order to avoid it, we need to consider a system of the third order. And how to prove that this system can be solved in terms of the quasi-determinants. So we also need to write down some restrictions on the initial conditions, kappa -1 and kappa 1, and they are huge. And because of this, I didn't write them here. But one can verify that under some conditions for initial functions kappa -1 and kappa 1, system 23 can be also solved in terms of quasi-determinants. Are there any questions?
Well, I think you can proceed.
Okay.
At least I have no questions.
Okay.
Well, we shall ask questions in the end.
Okay. Okay. So now we are. Yeah. The previous connection between the Toda chains and the Painlevé equations is useful if we would like to obtain some examples of fully non-commutative analogs for the Painlevé equations, but not to make some classification of such equations. But using the same idea, we are going to derive non-Abelian analogs for discrete Painlevé equations. And in order to do this, we need to present, we are looking for a non-Abelian analog for a two-dimensional discrete Toda lattice. So, and this analog is given by this expression. Here, the function theta is also an element of our ring, but now it depends on three parameters L, M, and N. It turns out that one can construct a quasi-determinant solution of this non-Abelian two-dimensional discrete total lattice and present the corresponding scalar or matrix Lex pairs. Well, in the non-Abelian case, how to reduce this equation to the well-known two-dimensional discrete total lattice? So we need to recall that quasi-determinants are a non-Abelian analog for a ratio of determinants. And here we have an expression for this function theta in terms of new function tau that also can be written in the determinant form because we look at the abelian case. Then, if we substitute this expression into this equation, we can write down classical two-dimensional discrete total lattice that is given by this very nice formula. But the discrete Painlevé equations, as their differential analogs, are non-autonomous, and we need to implement a non-autonomous constant in the total lattice. So we can make a scaling of the variable theta in the non-Abelian case, and in order to obtain a non-autonomous constant alpha element. Here alpha is a non-Abelian constant, and K1, K2, and K3 are commutative constants. L, M, and N are also commutative. Well, this equation, then now we are going to reduce this equation to a one-dimensional equation. So in order to do this, we consider a plane wave reduction, and then this equation can be reduced to a non-Abelian analog of the Thomas N sequence that can be written in this form. And again, how to derive from this equation, from this sequence, a Thomas N-like equation, we also need to look at a reduced change of variables of this form. And why we are interested in non-Abelian analog of the Thomas N equation? Well, because in the Abelian case, this sequence is related to some Painlevé equations, and we are going to make the same, observe the same relation in the non-Abelian case. So this relation is given by just change of variables. So we start from this non-Abelian analog of the Thomas N equation. Then we fix two parameters R and S, and for even N and for odd N, we have two different changes. This one and this one. And if we will do these changes, if we make these changes in this equation, then we can obtain hierarchies of Painlevé 1 equation and Painlevé 2. But instead of describing what they are, let us look at the example. Well, if we take n, the case when n is equal to 4, then this Somos n becomes the Somos 4 equation, and it can be written in this form. After this change, this Somos 4 equation can be written in terms of the new variable u sub m. Here, alpha m is a non-autonomous and non-Abelian constant. And equation 28, we will call non-Abelian analog for the Painlevé 1 equation. Well, how to rewrite this expression in the Abelian Painlevé 1 equation? Well, unfortunately, we can only start from the Painlevé 1 equation and then obtain this formula 28. So the Painlevé 1 equation is this one, or this sequence with the shifted m. They can be rewritten in this form if we multiply. If we divide these two equations by an appropriate expression, and if we look at the difference of these two guys, we can obtain our non-Abelian analog for the Painlevé 1 equation. So, So I just wanted to say that starting from the Abelian Painlevé 1, we can produce the equation 28. But unfortunately, we don't know how to rewrite equation 28 into Painlevé 1. But okay, let me make a few final remarks. Regarding a full classification of differential Painlevé systems, we have presented a very, very good criterion that is useful for classifying such equations with Abelian parameters. And our set contains all known systems of the Painlevé type and several new systems. These systems admit zero curvature representation, and they are closed under the degeneracy and under some group actions. But it's still necessary to study an non-Abelian analog of the Painlevé property for these systems, and it's also necessary to study recursion operators for the auxiliary autonomous systems of the Painlevé type, because we just looked at the simplest symmetries of non-Abelian Painlevé equations. Regarding the differential, the second part of this classification is the following. We would like to classify differential equations with non-Abelian parameters. probably our approach, our symmetry approach, will be useful in this classification problem. Let me stress that there are some examples of such systems of the Painlevé 5 and Painlevé 3 types, and of Painlevé 4, Painlevé 2, and Painlevé 1 types. So Painlevé an example for the Painlevé 1 system we have considered in the beginning of my talk. And now we are working on a classification problem on the following classification problem, namely, we would like to construct a criterion that will select a finite list of non-Abelian Painlevé equations with non-Abelian parameters that contains all known examples. Regarding the discrete Painlevé equations, we have derived several examples of their non-Abelian analogues, and in particular, we extended this scheme to the non-Abelian case. Namely, the scheme, namely, we study discrete non-Abelian Toda chains in the two-dimensional case. Then we considered the plane wave reduction to the Somos n equations, and using similar change of the variables as in the Abelian case, these Somos n equations can be rewritten to discrete Painlevé equations. And as a result, we have derived non-commutative hierarchies of the Painlevé 1 and Painlevé 2 equations. But we did not study their Lex pairs because because they are because we don't know how to rewrite how to obtain the corresponding Lex pair for the Toda chain with non-autonomous parameters. And we also did not study the continuous limits because starting from these non-commutative analogues for the Painlevé 1 and Painlevé 2 hierarchies, it's expected that we will obtain the corresponding hierarchies for the first Painlevé equation and for the second Painlevé equations. But to be honest, these two problems are still open in the Abelian case. And what else can we study? Can we do in this topic? We can interpret all our obtained systems as some symmetry reductions of the corresponding of some integrable PDEs, and we also may generalize some known results related to the commutative Painlevé equations to the non-commutative case. So let me stop here, and thank you a lot for your attention.
Thank you, Ira. There was a question from Sergei Pirogov. Sergei, would you like to ask it, or the question what is K, but I don't know which part of your
on which slides?
Sergei, would you like to ask the question? Is he? I am afraid that he is not here already. Well, let's keep it. Thanks a lot again. Questions, remarks, comments? Well, I have, maybe stupid question. Are there some examples or hints from not applications? Do such type of equations arise? I don't know, in physics, for example, or is just как это, игра в бисер, да? Of course, it's interesting. It's very interesting that there are so close analogs of classical objects in non-commutative algebra, but nevertheless, it is interesting whether such kind of objects arise, of course, not in practice, but in some related fields. Do you know examples of this type?
Well,
don't take it personally.
I understand. Well, what am I say here? I may say that that in the paper of Всеволод Adler and Vladimir Sokolov, the Painlevé non-Abelian analogues of the Painlevé 2 equation can be interpreted as the symmetry reduction of some integrable matrix PD.
Yes, but as I understand, maybe I'm wrong, their paper deals not with abstract algebra, but their non-commutativity lies in matrix algebra, or not?
Yes, they study these examples only in the matrix case, but
yes, I know that most works of this type, they are quite interesting, but they consider matrices, yes?
Yes.
Okay, thank you.
They worked with matrices, but examples when these equations appear in matrix, in physics, unfortunately, I don't know.
You don't know. Okay, so I thought, but nevertheless, it is interesting. More questions, more remarks. Well, Ир, спасибо большое. Thanks a lot. And you are welcome anytime you want to speak of some interesting new results. And good luck. So hopefully we meet in a week next Wednesday. Goodbye, and thanks for visiting our seminar. Goodbye.
Спасибо большое. До свидания.